In this set of videos, we're going to now start to look at the simple molecules as opposed to the giant structures. Now, if you remember back to the start of the course, the word molecule refers to one or more atoms that could be of the same element or different elements that are covalently bonded together. So when we use the word molecule, we must be only talking about covalent compounds. We cannot be talking about ionic or metallic. We can actually talk about covalent elements as well. So we're talking about things like Cl2, Br2, H2, or molecules like water, ammonia, methane. But they must have a covalent bond. And a covalent bond is described as a shared pair of electrons. So a double covalent bond would be 2 shared pairs and a triple 3 shared pairs. So the word pair is important because we're talking about a pair of electrons and we're sharing them, a shared pair. It occurs between non-metal atoms only. You can't have covalent bond to metals, so non-metal atoms. The unpaired electron in the orbital of one atom is shared with the unpaired electron in the orbital of another atom, and this is how they complete their electron configuration to that of a noble gas. So covalent bonds are shown using a line. So we could say if we took the fluorine-fluorine bond, we'd show it with a single solid line. So we're going to draw a diagram to show the bonding in each of the following molecules. What we're going to do is do a dot and cross diagram and then a stick diagram. So hydrogen has one electron in its outer shell. And so we could have one hydrogen with one electron and then a second hydrogen, and they're going to share this pair here so that they both get 2 electrons in their shell, which is a full shell for hydrogen because it only has the first shell. We could show that as a line between 2 hydrogen atoms. Chlorine, very similar, has, if we were to draw the stick diagram, it has a line. But if you think about it, chlorine's in group 7, so to get to a full shell, it needs to have 8. So it will be a little different. Remember, a dot and cross diagram must have dots and crosses. So we're going to do crosses, 7 crosses around one chlorine, and then share with another chlorine that has 7 dots. But all we see in the stick diagram is the shared pair as a line. H has 1 electron in its outer shell, and Cl has 7. And so we end up with H line Cl. Nitrogen has 5 electrons in its outer shell. So we go down putting 4, then a 5th. So it shares 3 with 3 separate hydrogens to get to a full shell of 8. If we were to look at that as a stick diagram, I'm actually going to show the shape of this because when we've only got 2 things in a line, like with the last 3 examples, they are just joined in a straight line. When we've got 4 atoms like this, 3 of them around a central one, they do actually take up a shape, which we will learn more about later. The shape of this molecule, it looks actually like a pyramid, and you'll learn why later. So this wedge is showing that the hydrogen on this bond is coming down and forwards. The sort of dashed line is going down and backwards. The one that's on the page is going in the plane of the page. And then there is a lone pair on top of nitrogen. I'm going to show that in an orbital. And so we've got this pyramidal shape to the ammonia model. Water, oxygen, is in group 6. So if we go around, go 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. We end up with 2 hydrogens, making oxygen have 8 electrons. Each hydrogen's got 2. If we were to draw that, it isn't in a line because actually these 2 lone pairs take up space. So I always think it looks a little bit like Mickey Mouse ears on the oxygen's head. It's got 2 lone pairs and 2 bonded pairs. So a lone pair here is a pair that isn't bonded. These are lone pairs. Pairs that aren't bonded around the central atom. And then the last one we've got, carbon is in group 4. So 1, 2, 3, 4. It bonds to 4 hydrogens. Hydrogen only wants to share 1 electron to get a full shell. Carbon needs to get from 4 to 8, so it needs 4. And so we get this dot and cross diagram. Its actual shape is called tetrahedral. So it kind of looks like the pyramidal one above, but with the fourth bond going up into the vertices of a tetrahedron. So these are all examples of dot and cross diagrams of simple covalent molecules. What about the ones that end up with double bonds? So oxygen is in group 6. To get to 8, it needs to share 2. Now, if the only other atom it's got to share it with is another oxygen, then it will have to form a double bond. So the O of itself has 6 electrons. It forms 2 bonds to make it to 8. How would we draw that in a dot and cross diagram? Well, we're going to end up with 2 shared pairs in the middle. Just put my oxygen a bit more central, and then the other one. And then 2 lone pairs on each oxygen. This is giving each oxygen 6 electrons. When we think about CO2, carbon is in group 4. For carbon to get from 4 to 8, it needs to make 4 bonds. Oxygen is in group 6. For oxygen to get from 6 to 8, it needs to make 2 bonds. So the carbon must be in the middle, and it must have a double bond to each oxygen. This way, each oxygen gets 2 bonds and the carbon gets 4. So how would that look in a dot and cross diagram? Well, carbon only has 4 electrons. It shares all 4 with the oxygens. Each oxygen has 6, so 2 lone pairs. So the crosses are belonging to the carbon, the dots are belonging to the oxygens. So there are 6 dots around each oxygen, 4 crosses around carbon, but if we look carefully, each atom now has 8, and so it has full shell. What about triple bonds? Well, nitrogen's in group 5, so to get to 8, it needs to share 3. If it shares them with another nitrogen, then they will each get 8. So we need to have 3 shared pairs between the 2 nitrogens. Now nitrogen's in group 5, so it has 5 electrons. If it's sharing 3, it only has 2 left. If we count around each nitrogen now, we've got 6 in the middle and then 7, 8 from the lone pair. When we think about HCN, so carbon is in group 4, so it needs to make 4 bonds. Nitrogen's in group 5, so it needs to make 3 bonds. Hydrogen's in group 1. It's not in a group, sorry. It needs to make 1 bond to get a full shell. So hydrogen wants to make 1, carbon wants to make 4, nitrogen wants to make 3. If we put carbon in the middle, make 1 to hydrogen and 3 to nitrogen, we are going to end up with the right number of bonds. So we're going carbon in the middle, triple bond to nitrogen, then nitrogen will have 2 other electrons. And then the carbon with the crosses makes a shared pair. I'm going to give hydrogen a triangle so it's different to nitrogen. And that is hydrogen's 1 electron sharing 1 of carbon's, and we get HCN. Now, there are a few occasions where we can't actually make it to this magic 8. How can we fill up the shell to 8? And that's simply because either it's not possible or we need to make more than 8 electrons to fill the shell. So boron is in group 3. Now, theoretically, it's a non-metal in group 3. It would need to get 5 electrons to fill its shell. Well, it can't get 5 electrons with regular covalent bonding because it's only got 3 to share. So if it's only got 3 to share, the maximum it could do is share 3 and end up with 6, which is what it does. So we have boron with its 3 electrons, so like 1, 2, 3, and each fluorine wants to gain 1 to get a full shell of 8, so it can do that. So, oops, we're going crosses for fluorine. So if we do that, we see that we've got 3 fluorines surrounding the boron. And that's how we would draw it. It takes like a trigonal shape, a flat trigonal planar shape. Now, SF6 is different in a different way because sulfur's in group 6. So theoretically, it would only want to make 2 bonds to get to A to get a noble gas configuration of P6. But because sulfur is in period 3 of the periodic table, a full shell for sulfur is not actually 8. A full shell, the third shell full, is 18 electrons. Now it can't get to 18 because to get to 18 when it's only got 6 electrons of its own is not possible because the maximum it can share is 6. So in this molecule, S is going to share its 6 electrons with 6 separate Fs. This is going to be quite tricky to fit in, but we'll just start and see how we get on, because we've got the first one of its 6, the second one of its 6, the third one. So these dots represent sulfur's 6 electrons. So I've done 4 of the 6. So we're going to do 5. And as you can see, I did say it was going to be quite tricky to fit in. So I've got to squeeze the 6th one in here. So the S is sharing with 6 fluorines. Now the shape that this takes up, which we're going to learn about shortly, is what's called an octahedral shape, because an octahedron has 6 vertices. So it looks like a square that is around the middle, so a flat square coming out of the page, and then a top and a bottom. So one up, one down, and then the 4 corners of the square sticking out. That's called the octahedral shape.